Hello guys, good morning, good evening, wherever you are in the world. Welcome to my channel. And if you are here to learn about the bracing of the steel frame structure, then you are in the right place, because in today's video, we will tackling another example problem. And this time we are determining the steel bracing member. So let's dive into the problem, and here it is. An HSS 8x8 1/4 section with a yield strength of Fy is equal to 46 kSi is used as a key bracing member in a structure with an 18 feet span and a simple end support, as illustrated in the figure below. So we are required to determine the design axial strength and the allowable axial strength using the appropriate AISC equation. In B, which is the one here, we will repeat E, but here instead we are using the table 4-4 of the AISC steel manual to determine the strength and the allowable strength of the member. So let's dive to the solution. And the section properties of HSS 8x8 by 1/4. The area is 7.1 square inch. Rx is equal to Ry is equal to 3.15 inches because we have the symmetrical profile. And the wall thickness is 0.233. Now this width to thickness ratio is equal to depth to thickness ratio, which is 31.3. And all these values are extracted from the AISC table. So the next one is to check the slenderness according to table B4.1a. So before going that table, guys, I would like to share with you regarding the connection of the bracing element. This bracing member is connected via a gusset plate from the top member of the frame, and to the lower portion of the columns we have the base plate here and anchorage to the pedestal, basically. So we are using this section HSS because this is a robust resistance to the buckling, local buckling, and the torsional resistance of the member. So if we proceed to the table to determine the slenderness, whether the member is slender or non-slender, in our case we are in case 6. So in case 6, because we are using the HSS profile, the width to thickness ratio, which is this one here, B/T should be less than or equal to the limiting ratio requirements for slenderness, which is 1.4 or the square root of E over Fy. So here in our calculation we have the width to thickness ratio is equal to 31.3 from here, less than equal to 1.4 square root of E over Fy is equal to 1.4 the square root of 29,000 over 46, which is Fy, is equal to 35.15. So as you can see here, this is our width to thickness ratio is less than to the limiting ratio of slenderness of 35.15, which is okay. So the section has no slenderness element because we are using this HSS, and that is the advantages of using this profile. Unlike the wide plans, we have the plans like that. So the next one is to check the effective slenderness ratio key. So in key, if you refer to the table, I would like to share with you this table, so you should be familiar on this one, because sometimes we have different boundary condition. But in our case, we are using this one, D, which is pin connected, so we use key value of 1. So here, the KL over R is equal to 1 times 18 feet times 12, because we are going to change this into inches to be consistent with our units. So 18 feet that is the length of our bracing, which is equal to 68.6, and it's less than to 200. This 200 is one of the requirements in the AISC requirements here, KL over R, preferably for members designed for compression, the effective slenderness ratio KL over R preferably should not exceed 200. That's why we have to check that one, particularly for bracing. So we are okay here for slenderness. So the next one is to check the elastic critical buckling stress based on the section E3 of the AISC manual. So we have the key value here, KL over R is equal to KL over RY is equal to KL over RX, because we have the symmetrical sections, is equal to 68.6. Then the next one is to determine the elastic buckling stress. So that formula here in the table, we have all the formula here that we are going to use to determine the design strength and the allowable strengths. That is under the section E3 of the AISC manual. So this is these are the formula. We have this one here, elastic buckling stress, and we have the criteria here to use this formula, and we have also, if the KL over R is greater than this equation, we have to use this one here. So KL over R should be less than or equal to 4.71 square root of E over Fy, or Fy over Fe, which is the elastic buckling stress, should be less than or equal to 2.25. So these are all the condition and criteria, guys. And go back to our equation. The elastic buckling stress Fe is equal to pi squared times 29,000 of elastic modulus of elasticity divided by 68.6 squared, which is this one from here, is equal to 60.82 KSI. And by the way, this equation is based on the AISC equation E3-4. So the next one is to calculate the flexural buckling stress FCR. This is the value that we need to determine, because that is the critical buckling stress that we are going to multiply the area to get the design strength and the allowable strength. So the criteria for that is equal to 4.71 square root of E over Fy, as we have seen that in the table from the AISC manual, is equal to 4.71 square root of 29,000 over 46 KSI, is equal to 118.26. And as you can see here, this is greater than to 68.6 from here, KL over R. Then the next one is to check this also. Fy over Fe should be less than or equal to 2.25. So in our case, 46 over 68.6 is equal to 0.57 less than to 2.25. So therefore, based on these requirements, we are satisfied with this criteria. So we can use this equation. This equation is FCR is equal to 0.658 to the power of Fy over Fe, then times by Fy. So we have to plug in all this value times 46, then we will get 33.52 KSI, and that you can verify that this equation from E3-2. So the next one, since we have determined the FCR, the critical buckling stress, then we can calculate the LRFD value, which is pi times the FCR times the gross area of the steel, which is 0.9 times 33.52 KSI times the area, 7.1 square inch, and that is equal to 214.2 keeps, and that is only for LRFD value, the design strength. The next one is to determine the allowable strength, the AISD. We have the FCR over omega times the area of the steel, which is 33.52 KSI over the omega factor of 1.67 times the 7.1 area of the steel square inch and equal to 142.71. So these are the value of the design strength, allowable strength using the equation of section A3 of from the AISC manual. So we are done with A. Now the next one is B. We are required to determine the strength using the table. So by the way guys, to use the table, actually what we need is only the KL and the profile of the strength. So here, if you want to determine this using the table, what you will need is the length of the member and what type of the HSS member. So here we are using the HSS. So go back to the table based on the AISC table here. If you can see here, we are using the HSS 8x8, and the thickness, the wall thickness is 1/4. Here, 1/4. Then you can check here the the value effective length KL. What you will need is the KL value, which is 18 in our case. So 18 feet. If you go across a little bit here in our under the column of 1/4 inches thick of our profile, you will get the AISD value of 143. The same what we have calculated in a longhand calculation. And the design strength, which is here LRFD 18. So these are the values. So if you have that the length of the column and the profile, you can really get the value of the strength, both AISD and LRFD right away. So this is how quickly and friendly to use the table. So back to our calculation. Here, these are the value from the table. We have the 214 and 143, the same value what we have calculated earlier. So guys, if you find this value or from the equation of AISC manual, you can compare that forces, the one if you are modeling the structure in whatever the program that you are using, then you can compare it from this value. Then you can determine whether the member is passing or not. If it is failing, maybe you can increase the thickness. It depends on your judgment. So that's all for this video guys, and if you find this video helpful and if you learn something out of this, then don't forget to like or subscribe so that you will be updated for the next upload. Thank you for watching. See you next time. Bye-bye.